Ever since humans looked up to the stars in the sky, they've wondered about the world they live in. Besides being inherently deserving, the search for ever more accurate descriptions of nature has brought us many of the technologies that we use every day. Everything from electricity to maglev train is only possible thanks to a fundamental understanding of physics. Quantum field theory is one of the major and latest milestones in this quest. Already in the 17th century, Newton formulated his theory on the movement of bodies. It worked wonderfully for everything from the motions of planets to the fall of an apple. However, in the early 20th century, classical theories were found to be insufficient to describe all aspects of nature. Einstein formulated his special theory of relativity for fast-moving objects. Quantum mechanics was invented for the smallest of scale. Quantum field theory succeeds them both, describing small, fast-moving objects. There are four fundamental forces in our world. Gravity keeps planets in their orbit. The electromagnetic force explains most everyday phenomena, such as why we can stand on the ground or see each other. The strong force holds particles together to form a stable nucleus, and the weak force explains radioactivity. Quantum field theory is the best theory to describe all forces except gravity in a unified picture. That name is composed of two parts that deserve enlightenment: quantum and field. Quantum means that a quantity has to take discrete values rather than continuous values. Imagine there's an inclined plane we can stand on at different heights. In the quantum world, when zooming in on the inclined plane, we find that there's actually a ladder. We cannot stand between the steps of the ladder. Those steps are so tiny that we did not notice their existence on a macroscopic scale, but they are obviously important in a microscopic world. The second part is field. A field associates a quantity to every point in space. There are different kinds of fields. For example, a temperature graph indicates the temperature at each point in space, and a wind map indicates the direction and the strength of the wind at each point on the map. Similarly, there are different kinds of fields that describe different kinds of particles. Just like the wind and temperature can interact to make a typhoon, different particle fields also interact to make new particles. In quantum field theory, elementary particles can be created or destroyed from a field. Particles are identical if they are generated from the same field. In addition, when energies are too little to cross an energy barrier, a particle cannot be created. Just like if we do not jump high enough, we cannot climb up the ladder. Moreover, particles can only be created or destroyed one by one, but not by half, like we cannot stand between steps of the ladder. Quantum field theory has been tested extensively in experiments. Measurements on electrons, one of the elementary particles, proved the quantum field theory calculation to be correct up to 10 parts in a billion. These days, predictions are being tested at unprecedented high energies with a 27 kilometers long particle collider. So far, quantum field theory passed with flying colors.